Welcome to the second session on planning and scheduling. We have 4 talks in this session, and we're going to start with a talk on action model acquisition from noisy plant traces by Hankz, Hankui Zhuo, and Kambhampati.
Good afternoon. I'm Hankz Zhuo from Sun Yat-sen University of China. My topic is about action model acquisition from noisy plant traces. This is a joint work with Professor Zhuo. Most work in planning community assumes complete domain models are given as input so that planning systems can solve planning problems. However, there is increasing awareness that building complete domains are difficult for domain creators, right? For example, web service composition, workflow management, etc. Attempts has been made to design systems to learn action models to help humans to create models. For example, slave, arms, and so on. However, these systems all assume actions in plant traces are observed correctly. In many real-world applications, actions are often observed incorrectly. For example, in urban disaster rescue environment, when observing these actions with sensors, noise is inevitably introduced when observing these actions. Okay. On the other hand, there have been many activity plan recognition approach that can be exploited to output plan traces. And these output plan traces are often with noise. Thus, in this work, we aim to develop an approach to tolerate noise in plan traces. Okay. So, what is the challenge? The challenge is how to capture information available behind noisy plan traces. We have observed that extending previous systems to handle noisy plan traces is difficult. For example, if we want to extend arms to handle noisy actions, it requires adding or removing constraints from arms to handle noise. So, either way of adding or removing constraints from arms is difficult to capture the distribution of noisy actions in the MACSAC framework, which is used by arms, right? So in this work, we aim to present a graphical model-based volunteering framework to tackle this challenge. Okay. The problem definition is like this. Given as input a set of plan traces, TO, which is with noisy actions. And the output is a domain model and stuff, which is composed a set of action models. Here is an example. The input is a set of plan traces. These plan traces is composed an initial state, the goal state, and an action sequence between the initial state and the goal state. Here, the red parts are noisy actions that should be on state AC and pick up B, respectively. The output is action models like this. When we here is an example of the action pick up, whose preconditions are on table X and empty clear X, etc. Okay. To solve this problem, we propose an approach called Aman. The intuition of our approach is that since states are dynamically changed by actions, and noise is introduced based on some unknown distribution. So we aim to explore a graphical model to capture the dynamics and noise, and then learn parameters of the graphical model to finally acquire the domain models. Specifically, we do the following steps. We first build a stack of candidate models from the set of noisy plane traces, and then we model the domain dynamic by building a graphical model. And next, we use a gradient as an approach to learn the parameters of the graphical model based on the candidate model and plane traces. And we finally output the domain model according to the learned parameters. As the fourth step, we aim to build candidate domain models. We first extract a set of action schemas and a stack of predicates, and then enumerate all possible action models based on the extracted action schemas and predicates. Typically speaking, we first scan each action and predicates in plane traces, and then replace the objects with their corresponding variables. For example, when scanning pickup A in plane traces, we will have action schema pickup X here by replacing the object with its corresponding variable. By scanning clear A in the initial state of plane trace, we will have clear X. That's one candidate domain model will be like this. Pickup X, whose precondition is clear X, right? Essentially. As we know, the set of candidate model could be large, right? So to restrict the number of candidate models, we impose validity constraints. That is, if P is an adding effect of A, then P should not be a deleting effect at the same time. If P is a precondition of A, then P should not be an adding effect. Finally, there is at least one precondition and one adding or deleting effect. These constraints are all from strict language descriptions. Okay. And we could also consider some domain companions constraints to further reduce the number of candidate models. Next, based on the candidate models and plane traces, we build a graphical model to capture relations between actions, states, and domain models, as shown below. Okay, in this graphical model, Xi is the ith state, and AI plus 1O is the ith plus 1's observed action, and N is a candidate model belong to the big N. And AI plus 1 is the I plus 1's true action here. Okay. Intuitively, the true action AI plus 1 conditionally depends on the domain model N here. And the current state Xi and the observed AI plus 1O. Yeah. Okay, so the corresponding conditional probability is like this. Okay. Furthermore, the new state Xi plus 1 conditionally depends on the domain model M, the true action AI plus 1, and the current state Xi. That is like this. Okay. Thus we can see that we can approximate the conditional probability of the unknown true plane trace T and the domain model N by using the structure of the Bayesian network and the sparsity of CBT, right, given the observed plane traces TO. Since we only focus on the deterministic models, there is only one state xi plus 1 when we're applying action ai plus 1 to the state xi, which suggests that p xi plus 1 given ai plus 1, xi and n should be 1. The value of this probability is 1. And other value for the probability is 0. On the other hand, we assume that each domain model N is also associated with a weight W. And then we define Pn by this formula. Okay. We can see that the larger the weight, the larger the Pn. We will choose the domain as the final output according to the weight. Then we can reduce this formula to this one. Okay. Furthermore, we model the distribution P ai plus 1 given xi ai plus 1 over the action space in a log linear fashion, which gives us the flexibility to incorporate a diverse range of features. And we can define this probability by this formula. Here, the big F is a k-dimensional feature representation. For example, F1 indicates the probability of ai plus 1. The value of F1 is 1 if ai plus 1 can be applied on xi according to F. And otherwise, it is 0. In our experiment, we set k to be 10 here. Okay, the theta is a k vector of parameters which will be learned in the next step. And the k, we also set the k to be 10 here. We can see that the conditional probability P only depends on the parameters theta and W. So we would like to learn the parameters. So to learn parameters, we sample a domain model to run the plane trace and get feedback to approximate the parameters. Specifically, we learn the parameters by maximizing the expected value function here. Here, RTM is a pre-defined Regulo function. In our experiment, we define RTM by number ATM times number PTM. Okay. Here, number ATM is the percentage of actions successfully executed in T, and number PTM is the percentage of proposition in the goal of T achieved after the last action. As we know, there is no closed form solution to this objective function, right? So, by observation, fortunately, we found that Regulo as an algorithm are capable of estimating the parameters theta and W. Thus, we perform the Regulo as an algorithm for a fixed number of iterations to approximate W and theta. And then finally, we simply select the domain model and start with the largest weight here. In our experiment, we evaluate Aman in the following aspects. We first compare Aman's accuracy with noisy plane traces to its accuracy with noiseless plane traces. And then we compare Aman to ARMS, a state-of-the-art method for handling noiseless plane traces. Finally, we evaluate Aman's learning time with respect to the number of plane traces. Okay. We test our approach in the following three IBC benchmark domains. And we generate 200 noisy plane traces by the following steps. We first generate 200 correct plane traces, and then randomly assign values to theta to calculate the conditional distribution P here. And then we sample 200 noisy plane traces TO based on the probability. And we define the accuracy by the total difference of coefficient effects between the learned model and the ground truth model. We first compare Aman's accuracy with noisy plane trace to its accuracy with noiseless plane traces here. In the picture, the light curve without noise suggests all plane traces are correct. And the blue curve with noise suggests all plane traces are with noise here. The accuracies of with noise become more and more close to without noise as the value of R becomes larger. Here, R is the number of iterations of the Grandian algorithm here. Why? This is because the distribution of noise becomes more and more close to the real distribution when the number of iterations increasing. Okay. And then we compare our approach to ARMS here. Since ARMS does not allow noisy actions in the input plane traces, we fetch both Aman and ARMS with noiseless plane traces to make the convolution fair by setting R to be 1,500. The accuracy of Aman and ARMS are very close to each other. You can see that from the picture. Okay, the rationale of this result is Aman exploits the reward function to enhance the model to best explain the plane traces, which is the same as ARMS. Since ARMS employs a set of constraints to acquire a model to best satisfy the plane traces. Finally, we test the efficiency of our approach here. We test Aman in the Bloxworth domain and by setting R to be 1,500. We can see the result is that the learning time generally increased linearly with respect to the number of plane traces. Okay. Yeah, in this work we presented Aman, a novel approach to learning action models given noisy plane traces. You know, our previous work only considered noiseless plane traces. And we also empirically demonstrated that Aman is effective in handling noisy plane traces. And it is competitive to ARMS here. We also saw our efficiency here. You're welcome to our poster section tomorrow morning. Thank you.
Questions?
Hi, can you go back to the model, to the graphical model?
The problem definition slide.
No, just
To the
that.
to that one, yes. I think yes, that one. That arrow that goes from the observation to the action, right? I think it should be the other way around.
This one.
Yes. The observation depends on the real action. And it's not like that. It's not like the real action depends on the observation.
No, I think we would like to look for the true actions here. So we will use the information from the observed signal and then to look for the true action. So we use this deduction.
That is the information because
Okay.
otherwise the marginal over the observation it will be the prior. Is that but it's like a hidden Markov model. So the arrow goes in the other direction.
But it doesn't have to, right? I mean, it's a base network. You don't have any causality built in there.
No, but it has to.
Thank you.
Just to, the direction of the errors doesn't have to conform to causality, but if you reverse it, you will have to add more errors there.
Yeah.
One, I think there would be.
Otherwise, the marginal over the observation it won't depend on anything. It will be the prior, right? That's not possible.
Since we first observe the signal by sensors, so
I mean, if you put the arrow in the other direction,
this direction, like
the observation is still going to depend. The action is
It's
going
actually
to depend
easier.
on the observation.
I think
You're not
it's-
losing that dependence. But the arrow has to go in the other direction.
But it doesn't change
I'm
anything.
sure of that.
They don't have.
Okay.
sorry,
So that means that I think that if you put the arrow in the other direction, you will increase the accuracy.
Yeah. So
You will have a better model, and then the accuracy should increase.
that's probably reasonable.
I think that's possible. Yeah. Yeah.
So, is there any other question? We have a few more minutes. Yeah.
Would it be difficult to generalize this to non-deterministic actions, given that it seemed like the only thing you did with determinism was to simplify this expression,
Yeah.
but in the end you're doing some sort of sampling-based optimization, so it may not matter if you have that term still in there?
Go ahead. I think the answer is it can be done, and he hasn't checked it yet. I mean, and you're right that pretty much the only place that particular simplification is being done is at this step. But he was comparing mostly to deterministic models and with arms and so on. So we don't know whether it will work just as well, but I think it should be possible.
So, if I can follow up on that,
Yes,
so
sir.
an additional generalization, could you also have noisy state observation or partial state observations in the same type
Possibly,
of model?
very much
I mean,
possible.
all of these things, of course, would make it more difficult and less efficient and so on, but in principle, they should fit within the same
Yes.
model.
It is, and in fact, I think there is some work on noisy state, based plan recognition. So he didn't focus on that in the paper more. But certainly, I think the model is general enough that that's certainly doable.
Okay, we're pretty much out of time, but maybe one last question. If you move to a probabilistic model and probabilistic actions and noisy observations, why not just use standard methods for learning DBNs? I guess there might be actually an advantage because of this you lose the notion of preconditioning because in a probabilistic model, basically, you just look at all the probabilities of the outcomes. And as conditional effects, it's more similar to conditional effects than to preconditions. But there might be actually an advantage still to use something like that with explicit preconditions, making the algorithm learn more efficiently.
Yeah,
Yeah.
I agree. Yeah.
Yeah.
Yes.
Okay, let's thank the speaker again.